In this episode, canal engineering on an immense scale.
This is one of the biggest projects ever made.
It is a big challenge, but that's what we pilots like. We like challenge.
Taking engineering to new heights.
The gates are enormous. The gates are like an 11-story building.
And the pioneering historic innovations.
It really is massive.
I'm really excited.
This is the basilica cistern. It feels more like a cathedral than a functional structure.
That made the impossible possible. The global shipping business is crucial to international commerce and prosperity. Sea freight accounts for around 90% of all world trade, and more than 10 billion tons of goods are transported by ship every year. For more than 100 years, the Panama Canal has provided a vital shortcut for shipping between the Pacific and Atlantic Oceans. The alternative is a costly detour round South America that takes over 2 weeks and uses over 1 million extra gallons of fuel. But by 2006, engineer Luis Ferreira and his colleagues are facing a giant problem.
The problem with the original Panama Canal is that the ships are growing, and the ship cannot fit through the existing canal.
Over the last century, ships have increased dramatically in size. This modern container ship can transport nearly 3 times the load of its predecessor, and is so immense it simply cannot squeeze through the original canal.
We need a bigger canal.
The solution? An engineering project of epic proportions. The Panama Canal expansion project includes new lock flights, with each lock the length of 4 football fields. The gates separating each chamber are as high as an 11-story building. 150 million cubic meters of earth were excavated to create new locks and channels. 4.4 million cubic meters of concrete were poured, encasing 192,000 tons of structural steel, creating a 77-kilometer-long canal capable of handling some of the largest ships in the world. But building it is no easy feat.
We have big challenge here. You have to understand the canal has to go over mountains in order to do this.
Today's container ships are so large that the expansion project must stretch beyond the canal itself to include the harbour approaches at either end. As contracts manager Jorge de la Guardia knows, modifying the landscape above and below the water here is a stupendous task.
We are looking here at the approach channel. Deepening and widening the channels of navigation presented quite a big engineering challenge because you have very hard rock and there are areas where you just have like a muddy surface. So that was the big challenge that we had.
But a supersized canal needs a supersized solution. This is D'Artagnan, one of the world's biggest cutter suction dredgers. And it is faced with one of the hardest problems of the build. At the Pacific end of the canal, tough rock on the seabed stands in the way of the new megaships.
We had to prepare the navigational channels for ships that are bigger and are deeper.
But D'Artagnan is designed to deal with even the toughest bedrock. It uses a computer-controlled rotating cutter tool like those on tunnel boring machines, to smash bedrock to smithereens, before sucking it up using a giant pump. Both the dredging and the excavations for new channels produce huge amounts of material and, as a result, create a seemingly impossible problem.
We needed a place to deposit the material that we were excavating, but to find areas where we could, deposit 50, 60 million cubic meters of material is not an easy thing.
An adjacent area of wasteland seems the perfect solution. But using it could literally have fatal consequences.
This was a contaminated area. This was not a place where you could walk or use it, because it was with unexploded ordnance.
The land had been used as a US Army firing range, leaving it littered with live ammunition. To find a solution, the engineers would need to draw on one of history's great innovators. Physicist Andrew Steele is travelling to the south coast of England, which in the 1940s was heavily fortified against a potential Nazi invasion.
When you've got a landscape that's littered with unexploded rounds, there's always the risk that someone's going to set one of them off and people are going to get killed. And armies have taken this and used it on purpose to create a weapon that can provide an unmanned line of defence, the landmine.
Laying hundreds of mines could create a formidable obstacle. This weight can be used to demonstrate the problem they present.
It's literally child's play to dig a hole, shove our mine underneath it, and then cover it all in sand. And now, it's pretty hard to tell there's anything there at all.
During World War II, thousands of mines were laid on Britain's beaches to protect against invasion. But the British faced a problem. The same technology was being used against them overseas. In North Africa, the successful German army protected its troops from counterattack using vast desert minefields. It took Józef Stanisław Kozacki, a Polish engineer who'd escaped to Britain, to come up with a solution.
This is what he developed. This is actually a slightly more modern version of Kozacki's device, and it uses the principles of electromagnetism and resonance to detect hidden metal objects.
Everything has a frequency at which it likes to vibrate, like a bell. Just like hitting a solid object, the electric current in a coil of wire will fluctuate at a particular frequency. It can also induce a current in a coil close to it. If the coils have the same natural frequency, the current in the second coil will be amplified or resonate, getting louder and louder.
What Józef Kozacki developed was a portable way of using these principles to detect metal. And what we've developed is a slightly simpler version to show you how it works. So what we've got here are our two coils, which we're going to be using obviously to detect the metal. We've also got an amplifier, and so you can hear what's going on, we've got a speaker as well. So let's plug this thing together and see how it works. We've got our two coils here and they're connected to this long section of wire. The first thing we're going to do is stick the output from one of the coils into the input of our amplifier. And the next thing we need to do is connect the output of the amplifier to the input of the other coil. So red into red and blue into blue. And what that means is we've set up the conditions for a feedback circuit. We've got the input of the amplifier being powered by one of the coils, which then goes out again, amplified, and powers the second coil. And that means that if there's enough connection between those two coils, we've got the potential for the same signal to go round and round and round in a loop and get louder and louder. Just like what happens if you take a microphone too close to a set of speakers. The final thing we need to do is connect it into the speaker, and then that will let us hear what it is that's going on in the circuit. So now we're going to go out and have a look for that mine. That low background hum you can hear is because those coils, they're just close enough together that they're almost on the point of feeding back. And all it takes is the presence of a little bit of metal just to increase the coupling between those two coils, and then we'll see if we can find that mine I laid. Oh, there we go. Yeah, I think we've got a bit of metal hiding under the sand here, so let me take off my mine detector. And then, there we go, dead easy. We found that fake mine that we planted earlier.
Józef Kosacki had invented the first practical, portable metal detector.
In 1942, Kosacki's mine detector was put into production. And in the autumn of that year, 500 of them were secretly shipped to Allied forces near Cairo.
It meant, at the legendary Battle of El Alamein, British engineers were able to clear a path through the German minefields, ultimately leading to a decisive victory for the Allies.
And this, the device he invented, was so successful that versions of his detector, first used in World War II, have been used for clearing minefields and detecting unexploded bombs and shells ever since.
On the Panama Canal expansion project, the modern-day equivalents of Kosacki's breakthrough provide the key to clearing the vast area of perilous unexploded ordnance.
We got companies that were experts at doing this. They would isolate an area, and then they were going very, very carefully, locating, and every time they located something, they marked it, and then other people came over to retrieve that. Then they piled them over together and blew them up if they were live.
In all, more than 3,000 pieces of live ammunition are removed and destroyed.
That was one of the biggest challenges because, thank God, nobody got hurt and we didn't have any accident on it. And we cleaned 460 hectares of unexploded ordnance.
But clearing the surroundings of explosives was just the start. To build facilities capable of accommodating ships like this, engineers have to overcome a series of epic challenges.
Pull to port.
And draw on innovators from history.
It's a beautiful example of engineering.
To make the impossible possible. The Panama Canal expansion project is being carried out so that today's supersized shipping can use this commercially vital shortcut between the Atlantic and Pacific Oceans. Sections of the original 1914 canal are being deepened and widened to accommodate giant container ships like this one.
Stand by on the starboard quarter. Stop the bow thruster. Bow thruster half to starboard.
Starboard quarter. The ship that can enter the existing canal can move between 4,000 to 4,500 containers. This ship is bringing between 12,000 to 13,000 containers.
But as Chief Engineer Ilya de Marotta knows, expanding the canal to accommodate this kind of ship means tackling Panama's geography.
The Panama Canal is a canal that moves ships from one ocean to the other one, Pacific Atlantic or Atlantic to Pacific, through a mountain range. So you have to put a ship through the mountains. So what do?
So how do you move a ship like this over the mountainous spine of the Americas? That would be an impossible challenge without the great innovators of history. Engineer Dr. Rhys Morgan has come to the Loire Valley in France to examine an innovation that changed water transportation forever.
At the start of the 17th century, King Henry IV of France had to rebuild a country that was ravaged by decades of religious wars.
Facing widespread food shortages, the king needed a surefire way of moving goods around the country.
Transporting goods over land was the obvious solution, but bandits roamed the countryside, and there was a limited amount of materials that you could carry. Worse still was the roads were so poor that your goods could easily be damaged.
France's network of rivers, however, offered a viable alternative. The king decided to build a canal to link the Loire and the Seine, connecting the north with the south. But there was a problem. Between the two rivers is a watershed rising up to 40 meters. 31-year-old hydraulics engineer Hugues Cosnier needed to find a way to make boats sail uphill. And what he came up with in the early 1600s was truly remarkable.
Here in the village of Rognier-le-Sept-Écluse is the most extraordinary example of what Cosnier achieved. It's a staircase lock, the first of its kind in Europe. 7 interconnected chambers enabled the boats to rise up the steep terrain. It's a wonderful and beautiful example of engineering.
Cosnier's staircase uses a sequence of lock chambers or pounds to lift boats over 3 meters at a time to traverse the slope.
I'm just really overwhelmed by the beauty and magnificence of this lock. It's just amazing to think it was built, almost 400 years ago. So how did it all work? Well, prior to this, there was a method of doing this called a flash lock, which involved a single step from the lower level to the higher level, but it was very dangerous. As soon as the gate was removed, there would be a torrent of water and the boat had to be pulled up through it. And then the gate closed behind it quickly. You can see the obvious dangers in this, and the boat could get damaged, the goods would be damaged. It was just a terrible way to lift the boat over the terrain. Cosnier's ingenious idea was to introduce a second gate. So that there would be a series of isolated chambers in which the water levels could be equalised and adjusted as appropriate. The boat would come in from the lower level and the gate would be closed behind it, sealing it into the chamber. The next stage was to slowly bring in the water until they will naturally equalise. Now the door could be easily opened without any water flushing through. And the boat could safely travel through.
By using a total of 36 pound locks, 12 on one side and 24 on the other, Cosnier conquered the 40-metre watershed and made the entire canal system possible.
Imagine thousands of canal barges moving their freight up and down this lock system. It must have been such a sight. A truly pioneering feat of engineering.
The new Panama Canal would need to take Hugues Cosnier's idea of a lock staircase and enlarge it to an extraordinary level. Chief engineer Ilya de Morota is in charge of building 2 new, enormous staircase locks, one at either end of the canal.
Building the new locks had a lot of great technological challenges. There's a lot of excavation that had to be done. It's a lot of earth moving. And not only was the earth moving, but the geology of the area, because you're going from sea level up to the mountains. So a lot of different types of soils were found.
The new locks require more than 20,000 workers, excavating 62 million cubic meters of rock and earth. That's 2.6 million dumper truck loads. They construct a total of 6 giant chambers, requiring 3.4 million cubic meters of concrete.
Needless to say, the structures are massive, unique designs. We have 3 chambers each raises the vessel 9 meters. So the vessel goes 27 meters high through an artificial lake, and it goes down the same 3 steps on the other side.
The epic construction is completed in June 2016. And this newly built colossal container ship is about to put it to the test. It will be the first time ever that this ship has transited the new locks.
Prueba popa sin miedo. Half to port, bow thruster.
The big challenge was to build a canal so we could fit this type of ship. This ship are going into a locks that has 427 meters in length by 55 meters in width.
Even though the locks are wider than an Olympic swimming pool is long, there are just centimeters to spare on either side of the hull, giving Chief Canal pilot Mario Chong little room for error.
Stop the thruster, hard starboard.
Hard to starboard! Hard to starboard!
It is a big challenge. It's a different type of vessel with more displacement, so you do have to be extremely careful and treat them different than the ships that we are used to at the old locks. Take longer to stop any erratic movement, lateral motion that you don't control properly. You can easily have an accident, run aground, because they're bigger. So it is a big challenge, but that's what we pilots like. We like challenge.
Mario will have to edge the ship through a flight of 3 enormous locks to reach the elevated section of the canal. But the size and scope of these locks creates other challenges.
Although we have locks around the world that are wider, we do not have any that are wider, longer, and deeper, and in addition, that have the 3 steps.
To solve these problems, engineers will look to the great innovators of the past.
It really is massive.
I'm really excited.
To make the impossible possible. The Panama Canal links the Pacific and Atlantic Oceans, and it's costing over $5 billion to make it big enough to accommodate cutting-edge modern container ships, like the 324-meter-long giant that pilot Mario Chong must guide through the locks today.
Half to port, bow thruster, half to port. Beautiful, sir. Well, right now we are in a process of this new generation of big ships. The most difficult part right now is the process of moving the ships through the locks, through the chamber. Keeping the vessel proper position inside the locks.
The 2 gigantic staircase locks, one at either end of the canal, are designed to lift the ship 27 meters, the height of an 8-story building, to reach the elevated section of the canal. But as Chief Locks Design Engineer Cheryl George knows, there's more to these new locks than just making existing designs bigger.
The biggest challenge that we encountered in the decision on the new locks was the type of gates that we would use.
Most locks use miter gates to create the chamber for raising and lowering boats.
Up we go.
The gates have the advantage that the upstream water pressure squeezes the gates together, minimizing any leaks, as long as you put the gates in the right way round. But once the locks get wider, so do the gates. And eventually they're so big, they take up a huge amount of room, and they get so heavy, they're difficult to support. Which is why engineers have thought about other ways to seal big locks. Restoration historian Tuija Lind is in Finland for a special event. she's come to witness the use of an innovative, watertight gate that only happens twice a year.
We are currently off the coast of Helsinki, approaching one of the largest sea fortresses in the world.
The sprawling citadel of Suomelina is home to one of the oldest operating dry docks in Europe, and today is the only opportunity to get boats in or out before winter. Key to the operation of any dry dock was the effectiveness of the gate keeping the sea out.
Traditional dock gates swung open like large double doors, but were difficult to maintain and put strain on the infrastructure of the dock. Worse still, some docks used temporary gates made out of wood and mud that had to be destroyed every time the dock needed reflooding.
In 1796, British naval architect Samuel Bentham came up with a revolutionary idea. And there's an example of Bentham's invention here in Suomelina.
It's amazing. It really is massive.
Called a ship caisson, it's an ingenious cross between a gate and a boat. And the secret of its success is about to be demonstrated.
Today we can see this 200-year-old invention in action.
Right now, the caisson gate is full of water, essentially a sunken boat. First, valves are opened, allowing water to flow into the dock.
I'm really excited. Now the water in the dock has reached the level where we can start pumping the water out of the gate, and then the gate starts floating.
It's not long before the gate becomes buoyant again.
Now the gate is floating, and I think we will soon release it and put it on the outer dock.
Despite weighing around 80 tons, the floating gate can be easily moved by pure manpower alone.
The Bentham's invention is in action, and it's amazing. It has really stood the test of time.
With the ship caisson safely out of the way, boats are able to enter or leave the dock as necessary.
It's really great.
When the dock needs to be used again, the caisson, which is floating, is manoeuvred back into the entrance. It's then flooded, settling into a slot in the stonework at the bottom of the dock mouth, forming a watertight seal. Water can then be pumped out of the basin to create the dry dock again. Bentham's idea of a floating gate changed the way dry docks were sealed forever.
This brilliant concept of a floating gate can be seen in canals and dockyards around the world to this day.
The new locks at the Panama Canal take the concept of the floatable caisson gate and blow it up to stupendous proportions. The expansion project uses 16 of these giants in total, all specially fabricated in Italy before being shipped to Panama.
The gates are enormous. The gates are like an 11-story building.
The gates all differ slightly in design, depending on which set of locks they're used in.
The ones at the lake are about 2,500 tons with all of their machinery, and the sea gates on the Pacific are about 4,400 tons.
Unlike Bentham's original caisson, these gates are designed to be rolled in and out of position. An operation that can only be achieved because they float.
The gates are supported on an upper and the lower wagon, but the wagons do not take 100% of the weight. The gates actually float, and only about 15% of the weight is actually carried by the wagons.
These enormous gates, they're also like a vessel, like a ship.
The rolling caisson gates also solve another significant problem with mitre gates. By having two of them at either end of each lock, any maintenance can be carried out on site without disrupting ships like this one moving through the locks.
At 12 o'clock, Alpha Tuck at 12 o'clock.
And that's crucial if the huge investment here is ever to be recouped.
We only have one lane. We cannot shut it down for anything. We have to be open 24/7.
But accidents are a fact of life, and shipping is not immune, as has been witnessed at the old Panama Canal locks. So how do you prevent a 200,000-ton, fully laden cargo ship like this one damaging itself as it edges through?
Stop the bow thruster, midships! Midships!
Once again, it would be impossible without the innovators of the past. Materials scientist Scott Ramsey is in New York City, where in the 19th century, concerns over the ivory trade led to the development of a world-changing material, due in no small part to the craze for playing billiards.
Some of the key players in the ivory trade were the billiard ball manufacturers. Tragically, one elephant tusk, such as this enormous yet accurately sized replica, can only be used to make 4 at most, and more often than not, a measly 2 balls. Faced with the loss of such a crucial resource and the possibility of going out of business, one billiard ball manufacturer, Phelan & Collender, located right here on 10th Avenue, offered a $10,000 reward to find an alternative material.
There had been primitive forms of plastic developed that century, like a product called Parkesine, but they were fatally flawed.
Parkesine and other early plastics were a combination of cellulose, nitric acid, and sulfuric acid. While they could be easily molded into a variety of things, they were prone to cracking, and so their broader application was quite limited.
After seeing the billiard ball manufacturer's advert for the $10,000 reward, John Wesley Hyatt, a printer and inventor from Albany, New York, started experimenting to see if different additives could improve the nitrocellulose material.
Hyatt discovered the importance of one key ingredient, camphor, found in the wood of a laurel tree. If we take this bowl of pasta to represent molecules of nitrocellulose, you can see in their current state they really stick together, and it wouldn't make a very useful plastic. So what we need is a short little molecule to get in between these and free them up so they can slide past one another. In modern terms, we call that a plasticizer, and in Hyatt's day, that was the camphor. So if we take this olive oil to represent the camphor, Hyatt realized by adding just the right amount, he could free the molecules up and create a moldable plastic.
Thanks to the camphor, Hyatt had come up with a material that could be molded, cut, shaped, and polished with ease. And he used it to manufacture not just billiard balls, but false teeth and piano keys too.
Hyatt had created a material that was strong, easy to form, and an ideal replacement for ivory. He called his material celluloid, and it's considered to be the forerunner of modern plastics.
It's a descendant of Hyatt's early plastic that makes it possible for today's colossal cargo ships to squeeze through the new Panama Canal locks.
It's important that we have protection for the vessels coming through the locks in the chambers. So we put fendering all over. There's about 6,000 fenders between Atlantic and Pacific to protect the vessel and the locks from hitting each other.
The fenders are made out of rubber with a sliding coat on the front. We call it the ultra-high molecular weight material.
Ultra-high molecular weight polyethylene is a hard-wearing thermoplastic, which creates very little friction when in contact with another surface.
Thruster, slow to port. Stop the thruster. Hard starboard.
The way we operate is the vessel goes and leans against the fenders a little bit while the water is going up or down in the chamber. So it's very important that we have that for protection of both the vessel and the lock.
It's thanks to pioneers of plastic like John Wesley Hyatt that Chief Pilot Mario Chong can get the enormous vessel safely through the locks. The low-friction thermoplastic coating on the fenders enables the hull to slide along their surface rather than catch, while rubber will absorb the force of any impact.
Captain, that's where it's supposed to be, okay? There are fenders there. We have to go towards the wall, sir. I cannot be away from the wall, okay? Hard starboard. Stop the bow thruster. I try to keep it closer to my side because I can't see what is on the other side. Okay, stop the thruster. Hard starboard. Hard to starboard. So far, the fenders have been doing their job. It's better to have it close to the wall that I'm seeing than having a guess of the space that I'm supposed to have at the other side. Thank you, sir.
So far, the expanded canal has operated trouble-free. But even when it operates smoothly, there's one issue that engineers have to address if the canal is going to run at all. To solve that, they'll have to look to the past.
It feels more like a cathedral than a functional structure.
To make the impossible possible. The Panama Canal Expansion Project is one of the biggest infrastructure projects ever attempted in Central America. The original channels are now deeper and wider, and gigantic new locks mean giant container ships like this one can use this commercially vital shortcut between the Atlantic and Pacific Oceans.
So, we're here. This is one of our ships, and that ship is paying $850,000 just to come through the canal.
But operating these enormous new locks has the potential to create a huge environmental headache.
One of the main resources for the canal to operate is water, fresh water. No water, no transit of ships. So water is one of our main concerns.
The canal relies on a man-made reservoir, Lake Gatun, to keep it running.
Push starboard. Hard to port. Stop the bow thruster. Gates are fully open. Here we go.
But the increased demand for water created by the new locks threatens both the canal and the population of Panama.
We had to be very careful on how we're going to use this water because, of course, this is bigger chambers, bigger vessels, they will use more water for the transit. The city of Panama and the city of Colón take water from Gatun Lake for drinking water. So it's of paramount importance not only for the transit of the vessels, but also for the water consumption of the cities. Worst case scenario would be we wouldn't be able to put enough big vessels through the new locks.
Confronted by a water conservation project of epic proportions, the engineers would once again look to the heroic trailblazers of the past to find a solution. Physicist Dr. Suzy Sheehy has come to Istanbul in Turkey in search of one of history's most extraordinary engineering feats. One that turned what was once a small settlement into a global powerhouse. And the secret lies hidden beneath the city streets.
This is the Basilica cistern, and it's a stunning example of Roman hydraulic engineering.
Built in the 6th century, it's the largest remaining of several hundred cisterns, or water-holding tanks, designed to keep water clean and prevent it evaporating during the hot summers.
It's amazing to think that this incredible place was built just to hold water. I mean, it feels more like a cathedral than a functional structure. It's 140 metres long by 70 metres wide, and there's more than 300 marble columns holding the roof 9 metres above the floor.
It was Roman Emperor Constantine who inspired this engineering wonder, when he decided to relocate the empire's capital away from Rome following a period of bloody civil war. But the city above here, Byzantium, now Istanbul, needed a water storage system. And the Roman engineers didn't disappoint.
The walls are almost 4 metres thick, and they're covered in a waterproof lime plaster. It could hold about 80 million litres of water. And when it was in use, this whole space would have been full.
Amazingly, the Basilica cistern forms the final section of a staggering 250-kilometre-long network of channels that still dominate Istanbul's skyline. They brought fresh water from the hills and forests into the city and turned it into one of the most important centres in the world. Incredibly, the whole system was so well engineered, it needed nothing more than gravity to deliver its precious cargo.
The hydraulic engineering that went into building this city is incredible. And without those engineers, this city would never have been the success that it was. And it's unbelievable to think that this beautiful structure was still being used by the Ottoman sultans nearly 1400 years after it was built.
Under the guidance of Chief Lock Design Engineer Cheryl George, the team on the expansion project are adapting the idea of a gravity-fed water holding tank to recycle as much of the water in the locks as possible.
The concept was to come up with the water-saving basins to limit the amount of water that is used with each lockage at the new locks.
Each of the new locks has 3 water holding basins attached to it, staggered at different heights. Instead of spilling water through the locks and then into the ocean, the precious contents are fed into these ponds. As the lock empties, the water is first channeled into the highest pond, then the middle one, then the lowest one. Only then is the water in the lowest part of the lock dumped into the next lock along. When the lock is refilled, the lowest holding basin is used first, followed by the middle one, and then the highest. Finally, the lock is topped up using water from the canal. The system, which only needs gravity and a complex valve control setup to operate correctly, is crucial to the viability of the new canal.
With this system that we have put into effect on these expanded locks, we're saving 60% of water, and that is a lot of water. And we've done it. It's working without any problem.
The whole system working in harmony allows pilot Mario to successfully guide new supersized cargo ships like this one through the system of locks and across the Americas in record time.
The most exciting thing about being a pilot at the Panama Canal is disembarking and just wave at the captain and the crew, you know, and seeing the ships going to sea. That's the best relief that I did make it safe transit, and the captain and the crew, you know, are on their new voyage. Stop the thruster. Captain, you got a new pilot.
The Panama Canal expansion project has been an epic undertaking. The engineering challenges in building a canal fit for purpose in the 21st century has stretched its makers to the limit.
This is something that we should be proud as engineers, because this is what we built.
Everything came together as it should. The work that we promised the country and the shipping industry that we would do, and to see it actually working and see the ships actually using the locks is really a sense of great pride for all of us.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, the engineers and designers of the Panama Canal expansion project have succeeded in making the impossible possible.
It's a dream job. It's a dream job for anybody, but for an engineer, it's like top notch.